Picture this: a vast, swirling black hole devouring light itself, a spacecraft tumbling toward a distant planet where time warps unpredictably, and a desperate mission to save humanity from extinction. These breathtaking scenes from Interstellar don't just belong to the realm of pure fiction. They were crafted with the guidance of some of the brightest scientific minds alive. But here's the question that lingers long after the credits roll. How much of this sci-fi masterpiece is actually rooted in real science? What if I told you that Interstellar isn't just a film, but a carefully calculated exploration of the cosmos, blurring the line between Hollywood spectacle and cutting-edge physics? From the moment it hit the big screen, Interstellar stood apart from other science fiction films. It wasn't content with just dazzling visuals or thrilling escapades. It aimed for something far more ambitious: scientific authenticity. Director Christopher Nolan teamed up with theoretical physicist Kip Thorne, a Nobel laureate, to ensure that every black hole, every wormhole, and every leap through space-time adhered to the laws of physics as we understand them. The result, a movie that doesn't just entertain but educates, pushing the boundaries of what we thought possible both in science and storytelling. So why does Interstellar deserve this deep dive? Because it's more than just a case study in scientific accuracy. It's a window into humanity's relentless quest to understand the universe. Whether it's the haunting beauty of Gargantua, the mind-bending concept of time dilation, or the terrifying reality of a dying Earth, Interstellar forces us to confront profound questions about our place in the cosmos. And as we peel back the layers of this cinematic masterpiece, we'll uncover just how much of its jaw-dropping science is grounded in reality, and where the film takes creative liberties to serve the story. Strap in, because this journey through the science of Interstellar will challenge everything you thought you knew about the final frontier. One of the most jaw-dropping concepts in Interstellar is the wormhole, a cosmic shortcut linking two points in space-time. But this isn't just sci-fi magic. Wormholes, or Einstein-Rosen bridges as they're formally known, emerge from Einstein's theory of general relativity. Picture space-time as a stretched bedsheet. Normally, traveling from one edge to the other means crossing the entire sheet, but what if you could fold it, piercing a tunnel through the fabric itself? That's the essence of a wormhole, a theoretical bridge where space bends so drastically that distant points touch. In reality, these cosmic tunnels remain purely hypothetical. General relativity allows for their existence, but stabilizing one would require exotic matter with negative energy, something we've never observed. Interstellar takes this idea and runs with it, depicting a spherical wormhole near Saturn, meticulously designed with Kip Thorne's input to stay true to the math. The film's version distorts light around it like a lens, creating that stunning visual of warped starfields, a detail grounded in actual physics. But here's where Nolan takes creative license. Wormholes of this size and stability are far beyond our current understanding. Realistically, they'd likely collapse instantly or be microscopic, not a convenient highway for spacecraft. The movie also sidesteps one of wormholes' biggest paradoxes: time travel. If you could traverse one, you might arrive before you left, violating causality. Interstellar focuses on time dilation near Gargantua instead, but the implication is clear. Wormholes aren't just space bridges, they're potential time machines. This duality between scientific ambition and narrative practicality makes Interstellar's wormhole a perfect metaphor for the film itself, rooted in real theory, yet unafraid to bend the rules for the sake of wonder. Gargantua isn't just another movie black hole, it's a scientific achievement. For the first time in cinema history, audiences saw a black hole not as a Hollywood special effect, but as astrophysicists predict it would actually appear. Christopher Nolan and his team worked closely with Kip Thorne to translate his equations into a visual masterpiece, resulting in a depiction so accurate it led to real scientific publications. But what makes Gargantua so groundbreaking, and how much of it aligns with our current understanding of these cosmic monsters? At the heart of Gargantua lies its accretion disk, the swirling maelstrom of superheated gas and dust spiraling toward the event horizon. Unlike the flat, Saturn-like rings usually seen in sci-fi, Interstellar's disk bends and warps dramatically, a direct consequence of the black hole's immense gravitational pull distorting spacetime itself. Light from the disk's far side curves up and over, creating that mesmerizing halo effect. This isn't artistic license, it's the product of Thorne's painstaking calculations, which the effects team used to generate the image pixel by pixel through custom software. The result, a black hole so realistic it changed how scientists visualize these objects in lectures and simulations. Then there's time dilation, one of the film's most haunting concepts. On Miller's planet, orbiting perilously close to Gargantua, 1 hour equals 7 years back on Earth. While the numbers are exaggerated for dramatic effect, the science behind them is sound. Einstein's theory of relativity tells us gravity slows time, a phenomenon confirmed by GPS satellites, which have to account for tiny time differences between Earth's surface and orbit. Near a black hole where gravity reaches extreme intensities, this effect becomes staggering. Interstellar takes this idea to its limit, showing how time doesn't just slow, it stretches like taffy, warping human lives in ways both tragic and awe-inspiring. But Gargantua isn't purely documentary, it's a blend of fact and creative necessity. Real black holes would likely shred anything approaching as close as the Endurance does, tidal forces stretching ships and planets into spaghetti long before they could orbit. And while the film's depiction of the event horizon, the point of no return, captures its eerie darkness, real physics suggests crossing it would be far less cinematic, with no sudden jumps into higher dimensions. Yet these tweaks serve the story without betraying core science, striking that rare balance between education and spectacle. What makes Gargantua truly remarkable is how it reshaped public understanding. Before Interstellar, black holes lived in textbooks and equations. Now, millions carry Thorne and Nolan's vision in their minds. The film didn't just entertain, it gave us a visceral sense of spacetime's flexibility, of gravity's power to twist the universe itself. And in doing so, it proved science fiction could be more than fantasy, it could be a gateway to the cosmos' greatest mysteries. Imagine stepping onto a planet where clocks don't just tick slower, they practically freeze. On Miller's world, every hour spent in that crushing gravity equals 7 agonizing years back on Earth. This isn't just sci-fi drama, it's one of Interstellar's most chillingly accurate scientific concepts. Time dilation near a black hole isn't hypothetical, it's a direct consequence of Einstein's theory of general relativity, warping the very fabric of reality itself. But while the film captures the emotional weight of this phenomenon, the real-world implications would be far stranger and more terrifying than what we see on screen. Let's break down the math behind this extreme time warp. Gravity doesn't just pull objects, it stretches time like taffy. The closer you are to a massive body like Gargantua, the more space-time curves, slowing time relative to observers farther away. For Miller's planet to experience a time dilation factor of roughly 60,000 to 1, it would need to orbit perilously close to the black hole's event horizon. Kip Thorne's calculations suggest the planet would circle at nearly the speed of light, completing an orbit every couple hours while the universe outside ages decades. But here's the catch, surviving those conditions would defy known physics. The tidal forces near a supermassive black hole, even one as gentle as Gargantua, would likely shred the planet apart long before such extreme time dilation could occur. The film glosses over another brutal reality, biological survival. Human bodies aren't built for environments where gravity's pull varies drastically over short distances. On Miller's planet, the difference in gravitational force between your head and feet could be so severe it would literally stretch you apart. a process astrophysicists grimly call spaghettification. And then there's the radiation. The accretion disk swirling around Gargantua would bombard the surface with lethal X-rays and cosmic rays, making those towering waves the least of your worries. What's even more mind-bending is how time dilation would distort perception. If you could somehow survive on the surface, your experience of time wouldn't feel slowed. Your heartbeat, your thoughts, all would seem normal to you, but watching the universe outside would be like hitting fast forward on reality. Stars would streak across the sky in seconds, and any communication with Earth would stretch into meaningless echoes. A single sentence radioed home might take years to transmit, turning conversations into lonely monologues across time. The film's portrayal of time dilation delivers an emotional gut punch, especially Cooper's devastating realization that he's missed decades of his children's lives. Yet reality would be even crueler. Relativity suggests that from Murph's perspective on Earth, Cooper's journey near Gargantua would appear in extreme slow motion. His movements would seem frozen, his ship barely inching forward over years. Meanwhile, from Cooper's viewpoint, Earth's history would flash by in a blur, civilizations rising and falling in what feels like days. This asymmetry isn't just theoretical, it's been measured in tiny fractions here on Earth. Atomic clocks on GPS satellites tick slightly faster than those on the ground, proving Einstein right in ways that keep our phones' maps accurate. Interstellar uses these scientific truths to craft a story about sacrifice and the irreplaceable nature of time, but it's worth pondering what the film didn't show. How would humans psychologically cope with knowing everyone they love is aging centuries in what feels like weeks? Could a society function if time itself became this unreliable? These are questions without answers for now, but they remind us that the universe operates by rules far stranger than fiction, and sometimes it takes a masterpiece like Interstellar to make us feel that awe in our bones. When Cooper slips beyond the event horizon of Gargantua, Interstellar takes its boldest leap into speculative science, the tesseract. This mind-bending sequence drops him into a dimension where time becomes a physical space he can navigate, a library of moments stretching infinitely in every direction. It's a breathtaking visual metaphor, but how much of this aligns with real theoretical physics? The answer lies in the controversial yet tantalizing idea of higher dimensions, a concept that stretches back over a century to the work of mathematicians like Bernhard Riemann and physicists like Theodore Kaluza. String theory, one of modern physics' most ambitious frameworks, suggests our universe might not have just 3 spatial dimensions plus time. It could have 10 or even 11. These extra dimensions would be curled up impossibly small, invisible to our everyday perception. But under extreme conditions, like near a black hole's singularity, they might unfurl, allowing access to what physicists call the bulk, a higher dimensional space where our entire universe is just one slice. This is where Interstellar's fifth-dimensional beings reside, entities who can manipulate gravity across time and space like we rearrange furniture in a room. The film's tesseract, a hypercube unfolding in 4 spatial dimensions, is a clever visualization of this idea. Inside it, Cooper sees time as a physical dimension he can traverse, peering into his daughter's bedroom like pages in a book. While no known physics proves such structures exist, the math allows for their possibility. Theoretical models suggest that in higher dimensions, gravity might leak between brains' membranes of reality, which could explain why it's so weak compared to other forces in our 3-dimensional experience. But here's where Interstellar diverges from hard science. The tesseract operates like a perfectly engineered communication device, allowing Cooper to transmit quantum data across time via Morse code on a watch's second hand. Realistically, even if higher dimensions existed, translating complex information through gravity waves with such precision would require technology or biology far beyond anything we can conceive. The film's beings seemingly orchestrate this with ease, bending physics to serve narrative necessity. Another fascinating departure is the portrayal of these higher dimensional entities. The film implies they're future humans who have evolved beyond physical form, a poetic twist that ties into themes of love transcending time. Yet most theoretical models treat bulk beings as entirely separate from our spacetime, not our descendants. Some physicists argue that any civilization capable of manipulating extra dimensions wouldn't resemble humanity at all. Their motivations and methods would be as incomprehensible to us as quantum mechanics is to an ant. What makes this sequence groundbreaking isn't just its scientific ambition, it's how it visualizes abstract concepts that even physicists struggle to picture. When Cooper floats between bookshelves representing different moments in time, we're seeing a four-dimensional object projected into three dimensions, much like how a shadow of a cube is a two-dimensional representation of a 3D shape. It's a rare case where cinema doesn't simplify science but elevates it, turning equations into emotional experience. Yet for all its brilliance, the tesseract sequence raises profound questions it doesn't answer. If these beings can manipulate gravity across time, why not prevent Earth's collapse outright? Why guide humanity through such an agonizingly slow salvation? The film suggests love and connection transcend dimensions, a beautiful idea, but one that sits at the edge of science and philosophy. This duality is Interstellar's genius. It uses cutting-edge physics as a springboard to explore timeless human dilemmas, proving that even in a universe of 11 dimensions, our greatest mysteries might still be the ones within ourselves. The barren wastelands we see in Interstellar didn't spring from pure imagination, they were ripped from the pages of American history. Decades before the film's dystopian vision, the Dust Bowl of the 1930s turned vast stretches of the Great Plains into a lifeless desert, forcing families to abandon their homes in a desperate exodus. Walls of dust towering miles high swallowed towns whole, turning day into night, while crops withered and topsoil blew away by the ton. Sound familiar? The parallels between this real-world catastrophe and Interstellar's dying Earth aren't accidental, they're a haunting warning about what happens when we push ecosystems past their breaking point. Scientists now recognize the Dust Bowl as a perfect storm of human recklessness and natural cycles. Decades of aggressive plowing tore up native grasslands that had held soil in place for millennia, while severe drought, possibly worsened by cooler Pacific Ocean temperatures, turned exposed Earth into powder. When the winds came, there was nothing left to stop them. Fast forward to Interstellar, and we see history repeating on a global scale. The film's blight, wiping out crop after crop, mirrors real-world concerns about monoculture vulnerabilities and soil degradation. Today, experts warn that over-farming, deforestation, and climate change could trigger new dust bowls, especially in regions already on the edge of desertification. But here's where Interstellar diverges from the past and aligns with dire future projections. The Dust Bowl lasted roughly a decade. The film's catastrophe is permanent. Modern climate models suggest that beyond certain thresholds, ecosystems may not recover. Like Cooper's world, we're flirting with tipping points where feedback loops, melting permafrost releasing methane, dying forests emitting carbon, could accelerate collapse. The movie's endless cornfields, humanity's last viable crop, reflect another grim reality. As temperatures rise and weather grows more erratic, our agricultural safety net shrinks. Scientists estimate staple crop yields could plummet by 25% within decades, leaving millions hungry. Yet Interstellar's greatest provocation isn't its science, it's the human response. The Dust Bowl spawned the Soil Conservation Service and new farming practices, proving societies can adapt. The film asks, what if adaptation isn't enough? What if Earth becomes not just harsh but fundamentally uninhabitable? That question lingers in today's debates about climate migration and space colonization. When Cooper laments that humans evolved to look at the sky, not down at dirt, he's echoing an uncomfortable truth. Our survival may depend on becoming something more than earthbound farmers. The Dust Bowl was a tragedy. Interstellar suggests the next one could be an extinction event unless we write a different ending. Those sleek, high-tech pods keeping Interstellar's crew in suspended animation for years might seem like pure Hollywood fantasy. But what if I told you scientists are actively working to make human hibernation a reality? The concept of cryogenic sleep has tantalized space agencies for decades, and while we're nowhere near the film's effortless deep freeze technology, recent breakthroughs suggest we're closer than you might think. Take NASA's ongoing torpor studies, for example. Instead of full-body freezing, researchers are exploring how to induce a hibernation-like state called synthetic torpor, slowing metabolism by lowering core body temperature just enough to reduce oxygen needs without causing tissue damage. It's not unlike how bears survive winter or how doctors already use therapeutic hypothermia after cardiac arrest to protect the brain. Early tests with animals show promise. Rodents placed in torpor for days wake up with no apparent harm. The challenge: scaling this to humans whose complex biology resists such drastic metabolic breaks. Interstellar glosses over the messy realities of long-term stasis. Real astronauts in torpor would need constant medical monitoring to prevent muscle atrophy, bone loss, or immune system collapse, issues the film's self-sustaining pods conveniently solve. Modern proposals involve rotating crews in shifts, with some awake to manage systems while others sleep, drastically cutting food and water needs for multi-year missions. Picture a Mars-bound spacecraft where the crew cycles through weeks of activity followed by months of metabolic slowdown, stretching supplies far beyond traditional limits. The film's most glaring omission might be the psychological toll. Unlike Cooper's crew, who wake up alert and ready, real astronauts emerging from torpor would face disorientation, temporary cognitive impairment, and possibly even memory gaps, side effects seen in patients recovering from prolonged medically induced comas. NASA torpor protocols include gradual rewarming periods and rehabilitation exercises, emphasizing that hibernation for space travel wouldn't be as simple as hitting snooze on a cosmic alarm clock. Yet the potential is staggering. Reducing metabolic rates by just 50% could have life support requirements, a game-changer for deep space exploration. Private companies like SpaceWorks Enterprises have already designed torpor-enabled spacecraft concepts, complete with snug pod layouts and automated medical systems. While we're decades away from the seamless stasis of Interstellar, each breakthrough inches us toward a future where crossing the solar system might not mean decades awake in a tin can, but rather closing your eyes near Earth and opening them at Jupiter. What makes Interstellar's vision so compelling isn't its accuracy, it's the question it forces us to confront. If we could sleep through the vast emptiness between stars, would the universe suddenly feel smaller? And more hauntingly, are we willing to surrender years of conscious life for the chance to reach worlds we'll never see in our waking lifetimes? The science of torpor may one day answer the how, but films like this remind us that the why will always be deeply, achingly human. In the vast emptiness of space, surrounded by the crushing silence of the cosmos, Interstellar's crew isn't alone. They have TARS and Case, two robotic companions that steal every scene they're in. Unlike the sleek, humanoid androids of most sci-fi, these machines move with a mechanical precision that feels both alien and strangely practical. Their blocky, rectangular frames might seem like a stylistic choice, but there's real science behind their unconventional design, a blend of military durability and advanced artificial intelligence that challenges our expectations of what robots should look like. Let's start with their physical form. TARS and Case aren't built to mimic humans. They're modular, reconfigurable machines capable of shifting their rectangular segments into different modes, walking, rolling, even acting as makeshift bridges or stabilizers. This isn't just Hollywood imagination, it's inspired by real-world military robotics. the US Army's research into battlefield robots has long favored simple, rugged designs over human-like features, prioritizing function over form. Think of them as high-tech Swiss Army knives, capable of adapting to unpredictable environments without the fragility of delicate joints or humanoid limbs. Their movement is another stroke of scientific realism. Instead of smooth, fluid motions, TARS and case move in precise, segmented steps, almost like a mechanical ballet. This reflects a principle in robotics called discrete locomotion, where machines optimize energy by moving in controlled, efficient bursts rather than continuous motion. Real-world prototypes like Boston Dynamics' legged squad support system use similar logic, favoring stability and power over grace. And their ability to run by unfolding into a rotating wheel, that's borrowed from transformable robotics, a field where researchers are actively developing machines that can reshape themselves for different tasks like NASA Super Ball Bot, designed to tumble across alien terrains too rough for traditional rovers. But what truly sets these robots apart is their artificial intelligence. TARS isn't just a tool, he's a character with personality, humor, and even moral flexibility. His infamous honesty-setting dial highlighting how trust and transparency become variables in human-machine relationships. This mirrors real debates in AI ethics. How much autonomy should machines have in life or death decisions? Can an AI truly understand sarcasm or loyalty? Modern AI like OpenAI's ChatGPT can simulate conversation, but lacks genuine understanding. Something Interstellar subtly acknowledges by making TARS would feel just a little too calculated, a reminder that even the most advanced robot is still following programmed parameters. The film also nails a detail most sci-fi ignores: sound design. Every movement TARS and case make is accompanied by whirring servos and clanking metal, an auditory reminder that these are machines, not magic. Real robots today, from industrial arms to Mars rovers, operate with similar mechanical noise, a byproduct of gears, actuators, and hydraulics at work. That intentional awkwardness makes them more believable, grounding their futuristic abilities in tangible, physical reality. Yet for all their realism, TARS and case embody one of Interstellar's most hopeful messages. Technology at its best doesn't replace humanity, it extends it. These robots aren't adversaries or cold, unfeeling tools. They're partners, saving lives with a mix of brute strength and unexpected tenderness. In a universe where black holes warp time and planets kill with crushing gravity, it's the machines built to keep humans alive that feel the most within reach, a reminder that the future of robotics might not look human at all, and that's exactly what makes them extraordinary. Imagine a city in space, not a cramped capsule, but a sprawling vessel designed to sustain generations of travelers on a centuries-long voyage to the stars. These are generation ships, a concept that sounds straight out of Interstellar's playbook, but one that scientists have debated seriously since the 1940s. Unlike Cooper's sleek endurance, these arcs would need to function as fully self-contained worlds, balancing fragile ecosystems, human social dynamics, and the relentless ticking of time. The challenges, they're as vast as space itself, and they force us to confront whether humanity could survive the journey, even if we somehow built the ship. First, the brutal physics problem: distance. Even reaching Proxima Centauri, our nearest stellar neighbor, would take roughly 6,000 years with current propulsion technology. That's longer than recorded human history. Generation ships sidestep the need for faster-than-light travel by accepting the timescale, becoming slow-moving islands where generations live, die, and pass the mission onward. But creating a closed ecosystem that lasts millennia isn't just about stocking enough food. It's about replicating Earth's intricate web of life in miniature. Think of Biosphere 2, the 1990s experiment where 8 people tried to live sealed inside a 3-acre artificial environment. Within months, oxygen levels dropped dangerously, crops failed, and ants hitchhiked in to devour their gardens. Now scale that disaster potential across centuries, and you begin to grasp the fragility of what generation ships attempt. Then there's the genetic hurdle. To avoid catastrophic inbreeding over dozens of generations, calculations suggest you'd need at least 500 carefully selected individuals, a number that balloons to tens of thousands if you want cultural stability and skill diversity. Cryogenic storage or artificial wombs might reduce the initial passenger count, but that introduces new ethical quagmires. Who decides which genetic traits get preserved? How do you prevent societal stratification between crew lineages over time? History shows even isolated communities like the Pitcairn Islanders descended into violence without external oversight. Now picture that tension in a metal hull where there's literally no escape. Perhaps the most chilling challenge is psychological. Humans aren't evolved for closed, unchanging environments. Studies on Antarctic winter over crews and submarine teams show that even highly trained professionals suffer mood crashes, sleep disorders, and irrational hostility in confinement, and their missions last months, not millennia. A generation ship's inhabitants might face the Earth sickness phenomenon, knowing their birthplace is an unreachable dot in the sky, their purpose reduced to maintaining systems for descendants who'll never see launch or landing. Without cultural or technological renewal from outside, stagnation becomes inevitable. Would later generations even care about a planet they've never seen, or rebel against ancestors who consigned them to a metal prison? Yet for all these nightmares, generation ships represent something profoundly human, the refusal to accept extinction. They're a hedge against planetary catastrophe, a bet that we can carry our civilization like a torch through the cosmic dark. Projects like NASA Hyperion suggest we're already tinkering with the building blocks: closed-loop air recycling, algae-based food systems, even proto-artificial gravity using rotation. The hurdles aren't just technical, they're philosophical. To build a generation ship is to admit Earth might not last, but that humanity must, and that's a truth heavier than any starship's hull. Deep beneath the rugged mountains of Colorado lies one of America's most secure military installations, Cheyenne Mountain Complex, a labyrinth of tunnels and chambers built to withstand nuclear blasts. This real-life fortress bears striking similarities to Interstellar's covert NAS, a base hidden inside an abandoned missile silo. Both locations embody humanity's instinct to burrow underground when facing existential threats, whether from Soviet missiles or a dying Earth. But here's what makes these parallels unnerving. For decades, governments have operated secretive facilities just like these, sparking endless conspiracy theories about what or who might really be hidden inside. Cheyenne Mountain isn't some shadowy rumor. It's the real-world counterpart to Interstellar's clandestine space program. Built during the Cold War to house NORAD, its 15 steel buildings sit on massive springs to absorb shockwaves, with half-mile-thick granite walls shielding personnel from electromagnetic pulses. The complex even has its own water supply and power grid capable of operating sealed for months. Sound familiar? Interstellar's NAS, a facility, mirrors this survivalist blueprint, complete with electromagnetic shielding to hide from a world that's given up on space exploration. The film's portrayal taps into a long history of governments preparing for doomsday scenarios far from public view, whether in man-made caverns or natural formations like Utah's NSA data center inside a mountain. This secrecy fuels speculation. Why would NASA need to operate in shadows if they're just launching crop-saving missions? Interstellar leans into legitimate public skepticism about classified space programs. Remember, the Pentagon only declassified its UFO investigation unit in 2020 after decades of denial, proof that even democratic governments withhold cosmic truths. Real-life equivalents abound. Area 51's infamous secrecy birthed wild theories about reverse-engineered alien tech, while Russia's mysterious Duga radar array was mistaken for mind control experiments. The film's conspiratorial undertones reflect our collective unease about who controls humanity's cosmic destiny and what they aren't telling us, yet there's a crucial difference between Hollywood and reality. Interstellar's hidden base exists because society abandoned science. Our real underground facilities thrive on government funding. The truth may be less about aliens than bureaucratic practicality. Secure locations protect sensitive tech from spies and sabotage. But that rational explanation can't dispel the allure of secrecy. When Cooper stumbles upon a secret space agency in an era of dust storms and food riots, it speaks to our deepest hope that somewhere brilliant minds are working on salvation, even if the world's too distracted to notice. That fantasy of guardians operating beyond public scrutiny is why Cheyenne Mountain and its fictional counterparts haunt our imagination long after the credits roll. The Lazarus missions represent Interstellar's most brutal scientific premise, sending astronauts one way into the unknown with no hope of return. While the film frames these journeys as heroic sacrifices for humanity's survival, the reality of such suicide missions would involve challenges far beyond what any Hollywood script could capture. Let's dissect what it would truly take to scout habitable exoplanets when coming home isn't an option. First, the logistics of one-way travel. Without the need for return fuel, spacecraft could theoretically be lighter and faster, but that advantage comes with horrific trade-offs. A Lazarus astronaut wouldn't just need life support for the initial voyage. They'd require sustainable systems to survive indefinitely on their target world. Picture this: instead of Endurance's sleek modules, imagine a ship crammed with hydroponic farms, 3D printers for spare parts, and emergency medical equipment capable of everything from dentistry to surgery. Even with perfect technology, isolation would gnaw at their sanity. Historical analogues like Antarctic explorers or nuclear submariners show that human minds fracture without companionship, something Interstellar hints at with Dr. Man's breakdown, but real psychological deterioration would likely strike much sooner. Then there's the scouting process itself. The film's thumbs-up/thumbs down evaluations of Miller's Waterworld and Man's Ice Planet oversimplify planetary science. In reality, assessing habitability requires years of atmospheric analysis, soil testing, and ecosystem mapping. A single astronaut couldn't possibly survey an entire alien world alone. They'd need autonomous drones, AI-assisted labs, and possibly even genetically engineered microbes to test soil chemistry. And what if the planet's deadly traits only reveal themselves seasonally? A world might seem temperate until its methane-rich polar caps melt in summer, flooding the atmosphere with poison. Without continuous long-term observation, something impossible for a lone scout, the data could be fatally incomplete. Communication presents another nightmare. Interstellar's quantum data link lets Cooper transmit findings from Gargantua, but real Lazarus missions would face light-year delays. A message from Proxima Centauri would take 4 years to reach Earth and another 4 for a response. By the time mission control spotted a problem, say dwindling food supplies, their astronaut would already be dead for years. This isn't just tragic, it's scientifically wasteful. Every failed Lazarus mission would represent the loss of irreplaceable cosmic knowledge, as decades of painstaking interstellar data vanish into the void with no one to interpret it. But the most chilling factor might be biological contamination. NASA spends millions sterilizing Mars rovers to avoid polluting alien ecosystems with Earth microbes. A human landing would inevitably seed the environment with bacteria, potentially dooming native life before we even discover it. And if the scout brought materials to build shelter, those metal alloys and plastics could leach toxins into alien soil for centuries. The ethical dilemma is staggering. In trying to save humanity, we might erase the very life we hope to find. Yet despite these horrors, the Lazarus concept isn't pure fiction. Organizations like the now-defunct Inspiration Mars Foundation once proposed one-way trips to the Red Planet. betting that volunteers would trade their lives for cosmic immortality. And therein lies Interstellar's genius. By pushing this idea to its logical extreme, the film forces us to ask, how much are we willing to sacrifice for survival? Not just as individuals, but as a species willing to condemn explorers to die light years from home. The answer may determine whether we reach the stars or remain forever bound to our pale blue dot. Cooper's desperate attempt to send quantum data from inside Gargantua back to Murph hinges on one of Interstellar's most tantalizing ideas, that gravity can transcend dimensions, carrying information across time itself. While the tesseract sequence leans into speculative physics, its foundation comes from real scientific debates about quantum entanglement and higher dimensional communication. But what separates Hollywood magic from genuine quantum theory, and could such interdimensional messaging ever be possible? Quantum entanglement, often called spooky action at a distance by Einstein, describes how particles can become linked so that changing one instantly affects its partner, regardless of distance. In theory, this could allow instantaneous communication, but here's the catch. You can't control or observe the entangled state without breaking the connection. It's like having twin coins that always land on matching faces when flipped, but you can't choose whether they show heads or tails. Interstellar circumvents this limitation by suggesting higher dimensional beings can manipulate gravity, the only force theorized to leak between dimensions in some string theory models, to transmit data. The film's pivotal moment, where Cooper jiggles the watch's second hand in Morse code using gravity waves, implies these beings found a loophole in quantum mechanics' no communication theorem. Real physicists have pondered similar ideas. Nobel laureate Gerard T. Hooft proposed that information falling into a black hole might leave gravitational imprints on its event horizon, a concept called holographic principle. Meanwhile, quantum gravity researchers speculate that singularities could act as bridges between branes, multidimensional membranes in string theory, potentially allowing data transfer. But these theories remain untested mathematical abstractions. The film takes creative license by portraying this transfer as precise Morse code, a human-readable signal. In reality, any data escaping a black hole would likely be scrambled into quantum noise, like trying to read a book after it's been through a shredder. The biggest leap lies in Murph's ability to decode the message. Quantum data typically requires specialized detectors to interpret. Imagine needing $1 billion particle collider just to read a text message. Yet Interstellar suggests love or intuition acts as the decoder, blending science with emotional resonance. This poetic liberty masks a deeper truth. If higher dimensions exist, their physics might be as incomprehensible to us as smartphones would be to medieval peasants. The film's genius is making cosmic-scale concepts feel personal, turning quantum entanglement into a father's last message to his daughter across the abyss of spacetime. What lingers isn't the plausibility, but the question it forces us to confront. If the universe permits such connections, are we simply too limited to perceive them? Interstellar reminds us that today's magic might be tomorrow's science, and that the line between them is thinner than we think. At first glance, Interstellar's claim that love could be a tangible, quantifiable force binding the universe seems like pure poetic fantasy. But what if science is closer to this idea than we realize? The film's most divisive moment comes when Brand insists love isn't just emotional, but a cosmic phenomenon we can perceive but not yet understand, capable of bridging space and time. Skeptics scoffed, yet cutting-edge neuroscience and quantum theories reveal eerie parallels to this seemingly mystical concept. Start with the brain itself. When neuroscientists map the neural pathways of deep emotional bonds, parent-child connections, lifelong partnerships, they find startling physicality. Love triggers measurable chemical cascades, oxytocin floods the system, dopamine reinforces attachment, and specific brain regions like the ventral tegmental area light up as if responding to a primal reward. Functional MRI scans show that heartbreak activates the same neural circuits as physical pain, proving emotions aren't just abstract, they're embedded in our biology. This raises a provocative question. If love alters matter at the molecular level within us, could it interact with the external universe in ways we haven't yet quantified? Quantum entanglement adds another layer to this puzzle. Particles separated by light years can instantaneously influence each other's states, defying classical physics. While this doesn't equate to human emotion, it suggests the universe operates on connections deeper than space-time. Theoretical physicist David Bohm proposed an implicate order, where separateness is an illusion and everything is fundamentally interconnected. In this framework, Cooper and Murph's bond isn't mere metaphor, it's a microcosm of universal entanglement, resonating across dimensions. The film takes this further by suggesting love could guide higher dimensional beings to specific moments in time, like Murph's bedroom, much like gravity warps spacetime around mass. Here's where science fiction diverges from fact. No experiment has shown consciousness affecting quantum systems outside controlled lab conditions. Yet the observer effect in quantum mechanics, where particles behave differently when measured, hints that perception might shape reality at microscopic scales. Interstellar extrapolates this to cosmic proportions, imagining a universe where love's observation collapses infinite possibilities into meaningful connection. Critics argue the film conflates metaphor with mechanics, but its real genius lies elsewhere. By framing love as both biological imperative and cosmic mystery, Interstellar bridges the gap between empirical science and existential wonder. Whether love literally bends spacetime may remain unproven, but the fact we can ponder it at all speaks to humanity's unique place in the cosmos. Beings evolved to feel deeply in a universe we're only beginning to decode. The Endurance isn't just a fictional spaceship, it's a carefully engineered vision of what interstellar travel might require, blending real physics with creative necessity. Let's start with its most striking feature, the rotating ring generating artificial gravity. Unlike the weightlessness of today's spacecraft, Endurance's crew walks normally along its curved interior thanks to centrifugal force. This isn't science fiction, it's straight out of Newtonian mechanics. Spin a structure fast enough, and inertia mimics gravity by pushing objects outward against the interior walls. NASA and private companies have explored this concept for decades, from the iconic spinning wheel of 2001, a space odyssey, to SpaceX's proposed Starship variants. But here's where Interstellar diverges from reality. The Endurance's ring spins just a few times per minute, creating smooth, Earth-like gravity. Actual designs would require a much larger diameter to avoid the disorienting Coriolis effect, where your head and feet experience different forces, potentially causing nausea. For a ring that size, you'd need a structure hundreds of meters across, something far beyond our current construction capabilities in space. Propulsion is another masterclass in balancing realism and drama. The Endurance relies on conventional chemical rockets for launch and maneuvering, but its journey to Saturn depends on a gravitational slingshot around Earth, a technique NASA's Voyager probes used to escape the solar system. Where the film veers into speculation is with the Ranger landers, which take off from planets with thick atmospheres and high gravity as effortlessly as helicopters. Real spacecraft would need exponentially more fuel for such feats, something the film handwaves with advanced propulsion. Yet even this isn't pure fantasy. Projects like NASA NTP nuclear thermal propulsion could theoretically offer higher thrust-to-weight ratios, while ion drives already used in probes like Dawn provide efficient, long-duration thrust. The Endurance's hybrid approach reflects a pragmatic future where different propulsion systems handle different phases of a mission. Then there's the ship's modular design, a cluster of habitats, landers, and command centers linked like a high-tech Tinker toy. This isn't just cinematic flair, it mirrors real plans for deep space missions. NASA's Lunar Gateway Station uses a similar modular approach, allowing components to be added or replaced over time. The Endurance's detachable landers also echo SpaceX's Starship concept, where reusable vehicles ferry crews between orbit and planetary surfaces. But the film's portrayal of rapid docking and undocking glosses over the complexities of orbital mechanics. Real spacecraft maneuvers are painstakingly calculated to conserve fuel, with minutes-long burns and precise alignment, not the Endurance's cinematic pivots and bursts of thrust. What truly sets the Endurance apart is its focus on long-term survivability. The ship carries cryopods for hibernation, closed-loop agriculture, and even a medical bay capable of complex surgeries. These touches ground the ship in the reality of multi-year missions, where psychological and physical health are as critical as engineering. Modern analogues like the International Space Station hint at these challenges. Astronauts exercise 2 hours daily to combat muscle atrophy, and every drop of water is recycled. The Endurance scales this up for decades of travel, anticipating problems we're only beginning to address, like radiation shielding and zero-gravity bone loss. Yet for all its realism, the Endurance embodies a paradox. It's simultaneously more advanced and more fragile than real-world proposals. Its spinning ring is elegant but mechanically vulnerable. One malfunction could send debris tearing through the hull. Real-generation ships would likely prioritize redundancy over grace, with backup systems for every critical component. And while the film's aesthetic, all exposed piping and industrial textures, feels authentic, actual spacecraft minimize moving parts to reduce failure points. The Endurance's beauty lies in its believability, not its practicality. It's a bridge between today's clunky prototypes and the sleek starships of our dreams, proof that the future of space travel might be stranger and more human than we've dared to imagine. The search for habitable exoplanets in Interstellar, Miller's Waterworld, Man's Ice Planet, and Edmund's Promising Haven feels like a high-stakes cosmic lottery. But how does this dramatic selection process compare to the meticulous methods real astronomers use to identify potentially life-supporting worlds? The truth lies somewhere between Hollywood spectacle and painstaking science, revealing just how far we've come in our hunt for Earth's cosmic cousins. In reality, scientists don't stumble upon habitable planets by sheer luck. They follow a rigorous checklist. The first filter is the Goldilocks zone, the orbital sweet spot where liquid water could exist. Too close to the star and oceans boil away, too far and they freeze solid. NASA Kepler telescope identified thousands of candidates this way, but Interstellar's trio of planets orbits Gargantua, a black hole, not a star. Here's where the film takes creative liberties. While black holes can theoretically have habitable zones where tidal heating replaces stellar warmth, the energy output would be chaotic and unstable. Real exoplanet hunters focus on main sequence stars like our Sun, where conditions are far more predictable. Next comes atmospheric analysis. Modern telescopes like JWST don't just spot planets, they dissect the light filtering through their atmospheres for biosignatures like oxygen, methane, or water vapor. A planet like Miller's, shrouded in endless oceans and ammonia-laced clouds, would likely be flagged as hostile long before any crew arrived. Man's frozen world presents another red flag. While icy moons like Europa intrigue scientists, a perpetually frozen surface suggests a lack of geothermal or tidal energy to sustain life. Interstellar handwaves these concerns with Gargantua's exotic physics, but real exoplanet researchers face a stricter burden of proof. The film's selection process also glosses over a critical real-world challenge: observational bias. Most exoplanets we've found are hot Jupiters, gas giants orbiting close to their stars because their size and proximity make them easier to detect. Earth-like worlds are needle-in-a-haystack discoveries, requiring years of repeated observations to confirm. When Brand's team declares Edmund's planet the clear winner, they're skipping steps real scientists can't afford to ignore. Projects like the Habitable Exoplanet Catalog prioritize planets with not just the right temperature, but stable orbits, magnetospheres to deflect radiation, and geological activity to recycle nutrients, factors barely mentioned in the film. What Interstellar gets hauntingly right is the emotional weight of these choices. When Romilly admits they're judging entire worlds on a year's worth of data, it mirrors real astronomy's struggle with limited information. Even our best telescopes offer pixelated glimpses, forcing scientists to make educated guesses. The film's tragic twist, that man's data was faked out of desperation, isn't just drama. It's a cautionary tale about confirmation bias in science. How many real exoplanet studies might be skewed by our eagerness to find Earth too? 0. The ultimate difference lies in stakes. Real exoplanet research unfolds over decades, with robotic probes doing the risky reconnaissance. Interstellar compresses this into life or death decisions, where one miscalculation drowns a crew or strands them in perpetual winter. Yet both share the same driving question. In a universe of infinite possibilities, how do we recognize home when we see it? The answer might not lie in flashy holograms or black hole orbits, but in the quiet, relentless work of scientists passing starlight for whispers of worlds beyond our own. The towering waves on Miller's planet aren't just Hollywood spectacle, they're a terrifying lesson in extreme astrophysics. Those skyscraper-sized walls of water rolling endlessly across the horizon embody one of the most brutal realities of black hole proximity, tidal forces powerful enough to reshape entire worlds. But could such monstrous waves truly exist, or did Interstellar take creative liberties with fluid dynamics? Let's dive into the nightmare physics of a planet orbiting too close to cosmic oblivion. First, consider the scale. Miller's waves are estimated to be over 4,000 feet high, nearly 4 times taller than the Burj Khalifa. For comparison, the tallest rogue wave ever recorded on Earth measured just under 60 feet. What could possibly generate such staggering liquid mountains? The answer lies in Gargantua's gravitational grip. Just as our moon tugs on Earth's oceans to create tides, a black hole's tidal forces would stretch and compress anything nearby, but with exponentially more violence. The math suggests Miller's planet orbits so close to Gargantua that the difference in gravity's pull between the planet's near and far sides could exceed its own surface gravity. This wouldn't just make big waves, it would distort the entire planet into an egg shape, with oceans sloshing violently from the deformation. Here's where the film's science holds up the wave's behavior. Notice they don't crash like earthly surf, but move in relentless, smooth walls. This matches how ultra-long wavelength waves would behave in shallow water with extreme gravity. The physics resembles tsunami dynamics, water molecules moving in near-perfect unison rather than breaking chaotically. Kip Thorne's equations dictated these details, ensuring the waves weren't just visually stunning but physically plausible. Within limits, but reality would be even more horrifying. For waves this size to persist, Miller's oceans would need impossible depths, likely exceeding the height of the waves themselves. Earth's deepest trenches only go 7 miles down. Miller's planet would require abysses dozens of miles deep to sustain 4,000-foot oscillations. Even then, the energy required would be cataclysmic. Realistically, tidal forces this strong wouldn't just make waves, they'd trigger permanent global tsunamis, with water potentially escaping into space during gravitational stretching. The planet might resemble a spinning water balloon more than a stable world. Another brutal factor, time dilation's hidden cost. While 1 hour equals 7 years elsewhere, the Ranger crew's brief stay means the planet's surface endures continuous tidal punishment for centuries from their perspective. Those waves aren't temporary, they're the eternal state of an ocean caught in gravitational torture. This explains the barren rock seen between surges. No coastal ecosystem could survive such relentless flooding. The cruel irony, these waves make Miller's planet simultaneously plausible and uninhabitable. While the tidal mechanics check out mathematically, the environment would be worse than the film shows. No breathable atmosphere could last long under such conditions, and any organic molecules would be shredded by the wave's kinetic energy. Interstellar gives us a poetic truth. The universe might forge breathtaking wonders, but they are often lethal to fragile human life. Those beautiful, terrible waves aren't just water. They're a cosmic warning about the price of orbiting too close to the abyss. Man's ice planet presents a landscape more alien than anything in our solar system. An endless tundra where the very clouds freeze midair, forming jagged spires that loom over the surface like shattered glass. While this surreal vista feels ripped from a nightmare, the science behind these frozen clouds isn't pure fantasy. To understand how a sky could turn to ice, we need to dive into the brutal extremes of planetary atmospheres and the delicate balance between pressure, temperature, and chemistry. The key lies in the planet's atmosphere or lack thereof. Unlike Earth's nitrogen-rich buffer, man's world appears to have a thin, wispy envelope of gases, likely dominated by substances like ammonia or methane that freeze at far higher temperatures than water. On a planet orbiting the cold outer reaches of a black hole's gravitational influence, surface temperatures could plunge below -100 degrees Celsius, cold enough to solidify gases that would remain vaporous even in Antarctica. But here's the twist: frozen clouds wouldn't just hover like Earth's cirrus formations. With insufficient atmospheric pressure to keep them suspended, they'd collapse under their own weight, fracturing into the jagged formations we see in the film, more like a frozen tsunami caught mid-crash than traditional weather. Real-world analogues exist, though none so dramatic. Saturn's moon Titan has methane clouds that drizzle liquid methane, while Pluto's nitrogen sky occasionally snows frozen particles. But for clouds to freeze solid across vast altitudes, you'd need an atmosphere so cold and stagnant that convection currents, the engine behind Earth's ever-changing skies, simply cease. Imagine a world where weather isn't a process but a frozen snapshot, where the sky itself becomes a fractured museum of its own demise. Yet Interstellar's vision glosses over one brutal reality: a planet with frozen clouds would likely be geologically dead. Earth's atmosphere stays dynamic thanks to heat from its core, and the sun removes those, and you get Mars, where thin clouds of carbon dioxide ice drift listlessly. Man's planet, though visually stunning, would be a cryogenic tomb, its frozen clouds less a weather phenomenon and more the corpse of a failed atmosphere. The film's haunting beauty masks a deeper truth. In the cosmic hunt for habitable worlds, sometimes the most breathtaking sights are the ones that scream, "Stay away." The giant spinning cylinder of Cooper Station might look like pure science fiction, but its design is rooted in decades of serious aerospace engineering, specifically the O'Neill cylinder concept first proposed in the 1970s. Picture a massive metallic tube 20 miles long and 5 miles in diameter, rotating steadily to create artificial gravity along its inner surface. Entire communities thrive on this curved landscape, with sunlight streaming in through vast windows running the station's length. This isn't just cinematic spectacle, it's one of the most plausible designs for permanent space habitats ever conceived. But how does Interstellar's vision stack up against real-world prototypes and the brutal physics of orbital living? Start with the basics of rotation-based gravity. The station spins at just the right speed to simulate Earth's gravity through centrifugal force, about one rotation every 120 seconds for a habitat of its size. Too slow, and residents would experience unsettling partial gravity. Too fast, and the Coriolis effect would make every movement nauseating. Here's where the film's design shines. Its sheer scale minimizes these issues. Real O'Neill cylinders were envisioned at similar dimensions precisely because larger structures reduce the disorienting side effects of spin gravity. Current research from groups like Arizona State University's Orbital Ranch project confirms this. Their proposed half-mile wide rotating habitats already show how nausea diminishes as diameter increases. Cooper Station takes this principle to its logical conclusion. Go big enough and the curve of the floor becomes virtually indistinguishable from Earth's flat horizon. Then there's the matter of sunlight. Unlike most sci-fi stations bathed in artificial lighting, Cooper Station uses ingenious mirrors to reflect and distribute natural sunlight, an idea straight from physicist Gerard O'Neill's original blueprints. The film's exterior shots show 3 vast rectangular mirrors pivoting independently, carefully angled to simulate day-night cycles inside. This matches real lunar habitat proposals where orbiting mirrors could illuminate polar bases stuck in permanent darkness. But Interstellar adds a hauntingly beautiful twist. Those same mirrors also frame glimpses of Saturn hanging in the blackness, reminding residents they're no longer on Earth. Where the film diverges from practicality is in its portrayal of open landscapes. Lush cornfields stretch into the distance with traditional houses sporting wooden porches, a nostalgic vision that ignores space farming's harsh realities. Real orbital agriculture would require intensive hydroponics under artificial light, with every gram of water meticulously recycled. NASA's Advanced Plant Habitat on the ISS reveals the truth. Space crops grow in cramped, high-tech chambers, not amber waves of grain. Similarly, the station's apparent breathable atmosphere spanning its entire volume wastes precious gas. Real designs would compartmentalize, minimizing air losses from inevitable leaks. Perhaps the most striking detail is how Cooper Station evolves over time. Early shots show it as a purely functional survival ark, all exposed infrastructure and temporary shelters. Decades later, it's become a thriving small-town America in space, complete with baseball fields and white picket fences. This progression mirrors real plans for generational space habitats, where initial industrial hubs gradually give way to comfortable living spaces as technology improves. The station isn't just a setting, it's proof of humanity's incredible adaptability, turning a metal emergency shelter into a home. Yet the unspoken challenge remains: scale. Building something 20 miles long would require mining asteroids for materials, as launching that much metal from Earth is laughably impractical. This is where Interstellar hints at off-screen advances. Presumably the same technology that built the wormhole also enabled massive construction projects in Saturn's orbit. Today's engineers are already experimenting with in-space manufacturing, from made-in-space's 3D printers to NASA's lunar regolith bricks. Cooper Station represents the endpoint of this trajectory, a triumph not just of engineering, but of our species' refusal to accept planetary boundaries. The genius of its design isn't in getting every technical detail right, but in showing how future humans might balance survival with sanity. Those vast windows looking onto Saturn aren't architectural indulgences. They're psychological lifelines, preventing the claustrophobia that plagues current space missions. The familiar homes and landscapes aren't nostalgia run amok, but careful preservation of what makes us human when everything else has changed. In the end, Cooper Station works because it understands that the hardest part of living in space won't be the physics, it'll be remembering how to feel at home. One of Interstellar's most mind-bending moments isn't about black holes or wormholes. It's a quiet scene in Murph's bedroom, where Cooper realizes he might have always been the ghost sending those cryptic messages. This is the bootstrap paradox in action, a causal loop where an event becomes its own cause with no clear origin point. Think of a time traveler giving Shakespeare his own works before he writes them. Where did the plays really come from? Interstellar applies this to gravity itself, suggesting the tesseract's fifth-dimensional beings might not be aliens at all, but future humans who have mastered spacetime to the point where they can manipulate their own past. Real physics grapples with these paradoxes too. Einstein's equations allow for closed time-like curves, paths through spacetime that loop back on themselves, but they come with philosophical headaches. If Cooper's actions inside Gargantua always destined Murph to save humanity, did free will ever exist, or is the universe prewritten with every choice just an illusion? Quantum mechanics offers a bizarre possible escape route, the idea that observing an event can alter its outcome. Some interpretations suggest causal loops might self-correct, collapsing into consistent timelines where effects neatly align with causes. It's like the universe playing editor, snipping away paradoxes to preserve logical continuity. The film's genius lies in dramatizing this without equations. Murph's realization that they are us mirrors a scientific hypothesis called self-consistent time travel, where any actions in the past must inherently avoid contradictions. A real-world analogy: imagine finding a sealed letter from your future self warning about a mistake. The very act of reading it alters your actions to ensure the warning was always sent. Interstellar's tesseract operates similarly, with Cooper's gravitational nudges ensuring a future where humanity evolves to build the tesseract in the first place. But here's where science balks. Such loops imply information can appear from nowhere, violating the conservation laws underpinning physics. The quantum data Cooper transmits, the key to gravity manipulation, has no discernible origin. If future humans derived it from his transmission, who created it initially? Kip Thorne himself admits this is the film's biggest scientific stretch, a necessary fiction to serve the story. Yet the paradox lingers as a tantalizing what if, reminding us that time's arrow might not be as straightforward as it seems, and that some mysteries bend as warily as space-time near Gargantua. While Interstellar presents wormholes and generation ships as humanity's escape plan, real-world astrophysicists are tackling existential threats with far more immediate, and sometimes startlingly simple solutions. NASA Planetary Defense Coordination Office operates like a cosmic early warning system, scanning the skies for asteroids on collision courses with Earth. But their toolkit extends far beyond mere detection. It includes audacious plans to nudge deadly space rocks off course using everything from nuclear explosions to robotic tractors. The Double Asteroid Redirection Test, or DART mission, proved this isn't just theory. In 2022, a refrigerator-sized spacecraft slammed into the asteroid Dimorphos at 14,000 miles per hour, altering its orbit. This kinetic impact technique, essentially a high-stakes game of cosmic billiards, could one day deflect a city-killer asteroid with enough lead time. For slower-moving disasters like climate collapse, NASA Earth Science Division deploys satellites like GRACE-FO to monitor groundwater depletion and glacial melt in real time. But some scientists propose even bolder interventions: space-based solar shades to reduce global temperatures, or genetically engineered phytoplankton blooms to absorb atmospheric carbon. These aren't sci-fi pipe dreams. The University of Hawaii's Lofted experiment recently tested an inflatable heat shield that could anchor future solar reflectors in orbit. Meanwhile, Breakthrough Starshot aims to launch gram-scale nanoprobes to Alpha Centauri using ground-based lasers, proving interstellar travel might not require massive ships but rather microscopic ingenuity. Perhaps most intriguing are the deep time survival strategies emerging from academia. The Svalbard Global Seed Vault safeguards crop diversity against agricultural collapse, while the Lunar Ark project envisions storing Earth's genetic blueprints in moon lava tubes, safe from planetary catastrophes. These efforts mirror Interstellar's preservation ethos, but with a crucial difference. Instead of fleeing a dying Earth, we're learning to armor it against the cosmic and environmental storms ahead. Because sometimes the most heroic solution isn't escaping gravity's grip, but fighting to remain anchored to the only home we've ever known. Gravity isn't just a force in Interstellar, it's the universe's ultimate communicator, threading through dimensions and time like a cosmic telegraph wire. The film's radical idea, that gravity can pierce the veil between higher and lower dimensions, might seem like pure fiction, but it's rooted in a century-long scientific quest to unravel gravity's true nature. While Einstein's general relativity paints gravity as the warping of spacetime itself, quantum mechanics insists it should behave like other forces, carried by hypothetical particles called gravitons. This schism between the two theories is physics' greatest unsolved puzzle, and Interstellar dares to imagine a future where we've cracked the code. Take the tesseract sequence, where Cooper manipulates gravity to send messages across time. This mirrors real theoretical work on gravitons particles that, if they exist, might not be confined to our three-dimensional space like light or matter. Some string theory models suggest gravitons could leak between dimensions in a hidden bulk space, just as ripples can pass through multiple layers of fabric. When Cooper rattles the watch's second hand with gravitational waves, he's exploiting this hypothetical loophole using gravity's unique position as the only force theorized to permeate all dimensions. Real physicists like Lisa Randall have explored similar ideas, suggesting hidden dimensions could explain why gravity is exponentially weaker than other forces. But Interstellar takes this further by giving gravity an almost sentient role. The film's fifth-dimensional beings don't just understand gravity, they've weaponized it, folding space-time like origami to rescue their ancestors. This poetic twist aligns with controversial concepts like the holographic principle, where our three-dimensional reality might be a projection from a two-dimensional surface encoded with gravitational data. It's as if the universe runs on gravitational code, and Interstellar's future humans have learned to reprogram it. Yet the film's most provocative claim isn't about physics, it's about connection. When Brand insists gravity transcends dimensions because it's the only thing that pulls us together, she's blending hard science with emotional truth. Just as gravity binds galaxies across unfathomable distances, it might also, in ways we don't yet comprehend, bind moments in time, memories, even love. That's where Interstellar transcends theory to touch something primal. In a universe of fleeting particles and entropy, gravity endures. It's the force that literally holds worlds together, and perhaps one day will help us reach them. Murph's breakthrough equation, the key to humanity's salvation, isn't just cinematic magic. Hidden within that scrawled handwriting lies a tantalizing glimpse into real theoretical physics' most ambitious frontier, quantum gravity. The film suggests this formula unifies Einstein's general relativity with quantum mechanics, solving how to manipulate gravity at microscopic scales. In reality, such a discovery would be the holy grail of modern physics, bridging the gap between the universe's vast cosmic dance and its tiniest subatomic whispers. The quantum data Cooper transmits likely represents what physicists call a graviton signature, the theoretical fingerprint of gravity's quantum carrier particle. Just as photons mediate electromagnetic forces, gravitons, if they exist, would be gravity's fundamental messengers. But here's why this matters. Detecting gravitons would prove gravity operates quantum mechanically like other forces, finally reconciling it with the standard model of particle physics. Imagine Murph's equation as a decoder ring for gravitational noise, isolating coherent signals from the quantum foam. Real-world analogs exist in LIGO gravitational wave detections, where impossibly faint spacetime ripples from colliding black holes are extracted from background noise a billion times stronger. Yet Interstellar goes further, implying the data enables practical gravity manipulation. This aligns with controversial theories like Heim's quantum field theory, which speculates about anti-gravity effects at quantum scales. Some fringe experiments even claim subtle gravitational anomalies in rotating superconductors, though mainstream physics remains skeptical. The film's genius is framing unification not as abstract math but as engineering. Murph doesn't just understand gravity's quantum nature, she harnesses it to lift entire cities into orbit, turning theory into literal uplift, the equation's most provocative aspect. Its bootstrap paradox origin, the quantum data has no clear genesis. Future humans derived it from Cooper's transmission, which came from their own future knowledge. This mirrors real debates about self-consistent physics models, where certain quantum states seem to self-reference into existence. It's as if the universe permits solutions that loop back on themselves, where knowledge transcends linear time. Whether such circular physics could ever manifest remains unknown, but Interstellar dares to imagine a reality where love and determination literally bend the rules of existence, not through magic, but through science we're only beginning to glimpse. The spinning endurance might look like a flawless feat of engineering, but there's a sneaky physics glitch hidden in its rotation, one that would turn the crew's artificial gravity into a nausea-fueled nightmare. Here's the problem. For a rotating space habitat to mimic Earth's gravity without disorienting its inhabitants, size and speed need to strike a delicate balance. The Endurance's ring is roughly 150 feet in diameter, spinning at a leisurely pace to create that smooth, Earth-like pull along its inner rim. But real-world physics says this setup would fail catastrophically, not in the Hollywood sense of explosive decompression, but in a far more insidious way. The Coriolis effect would twist the crew's sense of balance into knots. Let's break down the math. To achieve 1 g of artificial gravity, a 150-foot ring would need to complete a full rotation every 13 seconds. That sounds manageable until you consider how our brains interpret motion. At that scale and speed, the difference in centrifugal force between your head and feet would be stark enough to trigger constant dizziness. Tilt your head and the fluid in your inner ear would slosh unpredictably, convinced you're tumbling through space. Even simple actions like pouring coffee would defy intuition. Liquid would curve sideways as it falls, thanks to the habitat's rapid spin. Astronauts training in small rotating rooms on Earth report debilitating vertigo at just half this rotational rate, with some unable to stand after minutes of exposure. The Endurance's crew wouldn't be walking, they'd be crawling. The film's design overlooks another critical factor: structural integrity. A ring spinning that fast would experience tremendous stress, with every bolt and weld straining against centrifugal forces trying to fling the station apart. Real rotating habitats like those proposed by NASA and Nautilus X project prioritize massive diameters, think half a mile or more, to reduce rotational speed while maintaining gravity. At that scale, the Coriolis effect becomes negligible and structural loads distribute more evenly. The Endurance's compact size, while cinematic, would require materials far stronger than any known alloy to avoid buckling under its own spin. But the most ironic flaw, the Endurance's spinning sections contradict their own purpose. Early scenes show the crew living comfortably in the non-rotating command module, only visiting the ring for gravity therapy. Yet later, when Cooper docks the tumbling Ranger with the rotating ring, the film treats it like parallel parking, ignoring that mismatched spin rates would turn the maneuver into a deadly game of orbital bumper cars. Real spacecraft docking with rotating stations, like Russia's proposed Tsiolkovsky station, require perfectly synchronized angular momentum to avoid catastrophic collisions. These aren't just nitpicks, they reveal a deeper tension in Interstellar's scientific ambition. The film meticulously models black holes and relativistic time dilation, yet stumbles on basic Newtonian mechanics. Perhaps that's the price of storytelling. Physics bends for drama when humanity's fate hangs in the balance. But it's also a reminder that space travel's true challenges aren't always the cosmic ones. Sometimes it's the spinning floor beneath your feet that gets you. One of the most striking contradictions in Interstellar lies in its sound design, specifically the decision to let audiences hear the roar of engines and the crunch of docking maneuvers in the vacuum of space. Scientifically, this is pure fantasy. Sound requires a medium to travel through, like air or water, and the emptiness between stars offers nothing for vibrations to push against. Yet Nolan's choice to ignore this reality isn't lazy filmmaking. It's a calculated sacrifice of accuracy for emotional impact. Imagine the Saturn launch sequence in total silence. The visuals might be breathtaking, but without the thunderous bass of ignition or the creaking strain of metal, the scene would lose its visceral punch. This tension between authenticity and storytelling stretches back to the earliest sci-fi films. 2001, A Space Odyssey famously embraced silence, using classical music to underscore the eerie stillness of orbit. But Interstellar takes a different approach, blending realism where it serves the narrative like the muffled clangs inside helmets, with full-throated soundscapes when the drama demands it. The Endurance's spinning modules groan like a submarine under pressure, while Gargantua's Accretion disk emits a haunting, chorale-like rumble. These sounds aren't just auditory decoration, they're emotional shorthand, translating cosmic immensity into something our human senses can process. Real spacecraft would be unnervingly quiet to an outside observer. When the Ranger detaches from the Endurance, physics dictates only the faintest vibration from mechanical actuators, nothing like the metallic screeches we hear. Yet Nolan's sound team, led by Richard King, layered in organic textures, the groan of icebergs calving, the snap of frozen tree trunks, even the scream of a falcon diving. These earthly sounds ground the fantastical in the familiar, making the unreal feel tangible. It's a trick our brains unconsciously accept, much like how we perceive animations as alive despite knowing they're just pixels. The genius lies in what isn't heard. Notice how dialogue cuts out the moment a helmet disconnects, or how explosions in space lack the crisp crack of terrestrial detonations. These moments of selective silence remind us that Interstellar's soundscape is a translation, not a transcription, a bridge between the cold equations of astrophysics and the warmth of human experience. After all, if future astronauts could truly hear the cosmos, it might sound less like machinery and more like Hans Zimmer's pipe organ, a vibration so deep you feel it in your bones, resonating across the void. Let's crunch the numbers on Interstellar's cosmic road trip, because the journey from Earth to Saturn alone would be a marathon, not a sprint, with real-world propulsion. The film's Endurance crew reaches Saturn in a brisk 2 years, but today's rockets would stretch that into a grueling odyssey. Take NASA's Cassini probe, which launched in 1997 and took nearly 7 years to reach the ringed planet. And that was with gravity assists from Venus, Earth, and Jupiter acting as celestial slingshots. Without those boosts, the trip could have taken over a decade. Here's the brutal reality: chemical propulsion, the workhorse of modern rocketry, is laughably inefficient for interplanetary travel. The Saturn V rocket that sent Apollo to the moon burned over 2,000 tons of fuel just to escape Earth's gravity. To replicate Interstellar's direct trajectory to Saturn, you'd need a spacecraft carrying fuel tanks larger than skyscrapers, assuming you could even build engines powerful enough to push that mass. The film's Rangers and Endurance glide between planets with apparent ease, but current ion drives, like those on NASA's Dawn spacecraft, produce thrust equivalent to the weight of a sheet of paper. A human-rated mission would require years of patient acceleration to reach meaningful speeds. The math gets starker when we compare velocities. Cassini cruised at about 20 miles per second during its interplanetary coasting. Interstellar's ships likely traveled 10 times faster to hit that 2-year Saturn timeline, around 200 miles per second. Achieving that with chemical rockets would demand fuel loads so massive they'd collapse under their own weight. That's why real-world engineers dream of alternatives. Nuclear thermal propulsion could theoretically cut transit times in half by heating hydrogen to extreme temperatures, while Project Orion's abandoned concept of detonating nuclear bombs behind a pusher plate sounds like mad science, but was seriously studied in the 1960s for its potential to reach Saturn in months. Yet the film's most audacious timeline isn't the Saturn leg, it's the voyage through the wormhole to another galaxy. Even at light speed, crossing the Milky Way would take 100,000 years. The wormhole's magic is compressing that distance to months, but building such a shortcut would require engineering spacetime itself. Recent theories suggest microscopic wormholes might exist in quantum foam, but scaling one up to spacecraft size would need exotic matter with negative energy, something we've never observed. The takeaway: Interstellar's travel times aren't just optimistic, they're possible only with propulsion physics we can barely imagine. Today's best hope, fusion drives or antimatter engines, remain lab experiments. Until then, the stars remain stubbornly out of reach, and Saturn alone is a lifetime away. The film's real fantasy isn't black holes or fifth dimensions, it's the idea that crossing such distances could ever be routine. The human mind wasn't built for the crushing isolation of deep space, and Interstellar's portrayal of psychological unraveling under extreme stress cuts disturbingly close to reality. Take Dr. Mann, the Lazarus astronaut who fakes his planet's habitability data, then attempts murder when his deception risks exposure. His breakdown isn't melodrama, it's a textbook case of what happens when hope curdles into desperation after years of solitude. Real Antarctic winter overcrews Earth's closest analog to long-duration space missions report similar psychological fractures, irrational fixations, violent outbursts over trivial slights, and in one infamous case at Russia's Vostok station, a scientist threatening colleagues with an axe after losing a chess game. The film nails this descent by showing man's initial veneer of professionalism cracking under the weight of his lies, revealing a man who'd rather doom humanity than face being wrong. Romilly's quieter deterioration aboard the Endurance proves equally haunting. Stranded alone for 23 years in relativistic time while the crew visits Miller's planet, he appears outwardly composed, but the scattered textbooks and half-assembled models in his workspace betray a mind clinging to routine against creeping madness. Modern submariners confined for months describe eerily similar coping mechanisms: meticulously maintained logs devolving into incoherent doodles, sleep cycles fracturing under artificial lighting. NASA HIC's Mars simulation found that even highly trained volunteers began neglecting basic hygiene and equipment maintenance after 8 months of isolation, their motivation eroded by the pointlessness of repetitive tasks without tangible progress. Romilly's tragic end, killed by man's booby-trapped robot, becomes metaphor. The moment a mind stretched too thin by solitude finally snaps. What Interstellar gets especially right is the asymmetry of time dilation's psychological toll. Cooper's frantic return from Miller's planet, where he's lost 23 years in hours, mirrors the dissociation reported by ICU patients under sedatives or Arctic researchers during perpetual night. Your body's clock keeps one rhythm while the universe moves at another, creating a surreal detachment that sleep deprivation exacerbates. The film visualizes this brilliantly when Cooper watches decades of backlogged video messages from Earth, his face cycling through shock, grief, and helplessness as loved ones age before his eyes. Astronaut Scott Kelly described a milder version of this temporal whiplash after his year aboard the ISS, returning to find his twin brother visibly older while he'd experienced barely any subjective time passage. Yet the film's most psychologically acute moment might be its subtlest, Cooper's quiet rage when he learns the full truth about Plan B. His visceral reaction, "You knew I'd never agree to leave Earth if it meant abandoning my children," exposes the ethical fault lines in survival scenarios. Behavioral studies show that when forced to choose between abstract collective good and personal connections, humans overwhelmingly favor the latter, a phenomenon known as identity-based decision-making. This explains why real-life biosphere experiments collapse under interpersonal conflict, and why Martian colony plans account for familial units rather than purely mission-focused crews. Interstellar recognizes that no amount of theoretical training can override millions of years of evolutionary wiring. We'll always prioritize the faces we know over statistics we're told to save. The glaring omission, the crew's lack of psychological preparation for their mission's true stakes. Modern astronauts undergo years of resilience training for known stressors. NASA even uses underwater habitats to simulate confinement, but Interstellar's team appears blindsided by basic group dynamics. Real mission protocols would have included mandatory bonding exercises, conflict resolution frameworks, and contingency plans for irrational behavior. That said, the film's portrayal of flawed, emotionally compromised scientists makes for richer drama than sterile professionalism ever could. Their mistakes feel human because we recognize our own fragile minds in their struggles, and that may be Interstellar's most terrifying realism of all. There's a moment in Interstellar that cracks open the heart of relativity, not with equations, but with the raw, unfiltered agony of a father watching his child grow old without him. Cooper's encounter with the video messages from Earth isn't just a plot device. It's a visceral collision of Einstein's physics and human emotion, where time itself becomes the antagonist. As he scrambles to absorb 23 years of missed birthdays, graduations, and grief in a single sitting, we're confronted with the cruel irony of relativity. The same laws that let him cross the cosmos also steal his chance to be there for the moments that matter. The science behind this tragedy is chillingly precise. Time dilation near Gargantua means Cooper's hours on Miller's planet equate to decades on Earth. But the film's genius lies in how it visualizes this asymmetry. Each message from Murph arrives like a hammer blow, her face aging in jumps, her voice deepening with resentment, her eyes hardening from betrayal. From her perspective, Cooper's journey unfolds in agonizing slow motion. His ship barely moves against the starfield, as if he's frozen in amber. Meanwhile, for him, Earth's history accelerates into a blur, with entire lifetimes compressed into minutes. This isn't just theoretical. Real astronauts on the ISS experience microversions of this dissonance, returning home to find their children subtly changed, their absence leaving gaps no video call can fill. What makes Cooper's torment uniquely harrowing is the one-way nature of the communication. He can't interrupt, explain, or apologize as Murph's messages play. He's a ghost in her timeline, screaming across a gulf relativity won't let him cross. Modern psychologists call this temporal dislocation, a phenomenon observed in long-distance submariners and polar researchers, where delayed communication fractures relationships. But scale that isolation to interstellar distances, and the emotional math becomes unbearable. Every frame of Murph's videos carries unspoken questions. Why did you leave? Did you know this would happen? Cooper's helplessness mirrors a parent trapped behind soundproof glass, pounding on walls their child can't hear. The film's sound design heightens this brutality. Notice how the messages play without pause, no buffering, no static, just relentless chronological momentum. It's a directorial masterstroke emphasizing time's indifference. Real deep space communication would be riddled with lag and degradation, but here the clarity is the horror. We hear Murph's breath catch as she mentions her brother's death, the wobble in her voice when she finally abandons hope. These aren't transmissions, they're time capsules from a life Cooper can never reclaim. Yet the cruelest twist lies in the asymmetry of their grief. Murph lives with the slow burn of abandonment, while Cooper's loss hits like a supernova, all 23 years collapsing onto him at once. Studies on sudden bereavement versus prolonged illness show this dichotomy in miniature. The brain processes trauma differently when stripped of the chance to adapt. Cooper's staggered reactions, denial, bargaining, rage mirror the 5 stages of grief, but compressed into 90 seconds of screen time. It's relativity as emotional combat, where time bends not just light but the very shape of love. Physics offers cold comfort here. Einstein's equations permit no preferred frame of reference. Both Cooper's and Murph's experiences are equally real. But Interstellar forces us to sit with the human cost of that symmetry. The film's most devastating moment isn't the black hole or the wormhole. It's the quiet click of the final message ending, leaving Cooper adrift in the silence between star systems, holding nothing but the weight of everything he's lost to the abyss of dilated time. Before settling on the tesseract's mind-bending finale, Christopher Nolan and Kip Thorne wrestled with several alternate endings, each rooted in plausible physics but ultimately rejected for narrative or scientific reasons. One early concept involved Cooper sacrificing himself to slingshot the Endurance toward Edmund's planet using Gargantua's gravity, a maneuver mirroring real astrophysics. NASA Voyager probes used similar gravitational assists from Jupiter and Saturn, trading orbital momentum for increased velocity. But here's why this ending didn't stick. The math demanded Cooper's ship approach the black hole's event horizon too closely, where tidal forces would have shredded it long before achieving the necessary velocity boost. Another discarded idea leaned into the eerie phenomenon of spaghettification, the vertical stretching and horizontal compression objects experience near black holes. Storyboards show Cooper's body elongating grotesquely as he transmits data back to Murph, his atoms unraveling into cosmic strings. While scientifically accurate, this horrific transformation is precisely what would occur during a real black hole plunge. Thorne argued it undermined the emotional payoff. A protagonist dissolving into quantum spaghetti made for compelling horror but poor closure, reducing Cooper's arc to a gruesome physics demonstration rather than a cathartic reunion across dimensions. The most tantalizing rejected ending involved quantum superposition, Cooper surviving inside the singularity as both a corpse and a living observer simultaneously. This paradoxical state drew inspiration from the Schrödinger's cat thought experiment, where particles exist in multiple states until observed. Early drafts depicted Murph receiving Cooper's data bursts while mission control simultaneously recovered his lifeless pod, leaving his fate ambiguously unresolved. Nolan ultimately vetoed this approach for being intellectually satisfying but emotionally hollow. Audiences needed clearer resolution after the story's emotional investment. Contrast these with the chosen fifth-dimensional resolution, which cleverly sidesteps scientific nitpicks by operating beyond known physics. The tesseract allows Cooper to influence the past without violating causality. His actions were always part of history's fabric, neatly avoiding the grandfather paradox. Where the alternate endings clung to hard physics at the cost of narrative satisfaction, the final version bends reality just enough to serve the story's heart, a father's love transcending space-time. The genius lies in making the least scientifically verifiable ending feel the most truthful, because sometimes the equations of human connection outweigh those of relativity. Interstellar didn't just captivate audiences, it rewrote the playbook for how blockbuster cinema could ignite public fascination with cutting-edge science. Before its release, topics like gravitational time dilation and higher dimensional physics were confined to textbooks and academic lectures, dismissed by many as impenetrable abstractions. Yet in the span of a single theatrical run, Christopher Nolan and Kip Thorne transformed these esoteric concepts into water-cooler conversations, proving that even the most complex theories could resonate emotionally when framed through human struggle. The film's secret weapon, its willingness to treat astrophysics not as exposition, but as the narrative engine driving every character's choices and sacrifices. Consider the ripple effect in science education. Following the film's debut, universities reported surges in enrollment for introductory relativity courses, with professors citing Interstellar as students' gateway to the subject. Physics educators quickly adopted Gargantua's stunning visuals as teaching tools, replacing outdated textbook diagrams of black holes with frames from the movie. Even the film's creative liberties, like the amplified time dilation on Miller's planet, became springboards for classroom discussions about the real science behind the fiction. Lectures that once put students to sleep now buzzed with debates over the feasibility of wormholes or the ethics of one-way space missions. the American Physical Society noted a measurable uptick in public engagement with their outreach programs, crediting the film for making theoretical physics feel urgent and tangible. But the impact extended far beyond academia. Thorne's collaboration with double negative visual effects birthed a revolutionary software that rendered light around spinning black holes with unprecedented accuracy. These simulations didn't just look pretty, they generated legitimate scientific insights, leading to 2 peer-reviewed papers in classical and quantum gravity. For the first time, Hollywood CGI contributed directly to astrophysical research, revealing how light from accretion disks would lens around a rapidly rotating singularity. Scientists used these models to refine their understanding of how to interpret real telescope data from black hole observations, blurring the line between entertainment and empirical discovery. The film also reshaped science communication itself. Neil deGrasse Tyson famously quipped that Interstellar did more for public understanding of relativity in one summer than decades of PBS specials. Science YouTubers like Veritasium and PBS Space-Time saw their viewership skyrocket with Interstellar-themed breakdowns, proving there was an appetite for deep dives when audiences cared about the narrative stakes. Even NASA capitalized on the momentum, releasing educational materials that compared the film's scenarios to real missions like the James Webb Space Telescope. The European Space Agency went further, hosting public screenings followed by Physicist Q, and as an outreach model now standard at science museums worldwide. Perhaps most unexpectedly, Interstellar influenced policy and funding. The film's haunting depiction of a climate-ravaged Earth lent visceral weight to discussions about planetary sustainability, cited by multiple climate researchers in congressional testimonies on environmental research budgets. Meanwhile, its portrayal of a desperate space exodus reinvigorated debates about the importance of multi-planetary species planning, with figures like Elon Musk referencing the film when advocating for Mars colonization. The line between fiction and advocacy blurred when the Breakthrough Starshot initiative aiming to send nanocraft to Alpha Centauri adopted the tagline, making Interstellar's vision a reality. Yet the film's greatest legacy lies in how it redefined what science storytelling could achieve. By anchoring cosmic phenomena to a father's love for his daughter, it proved that the coldest equations of physics could carry emotional heat. Where documentaries explain, Interstellar made audiences feel the gut punch of time slipping away, the terror of the unknown, the awe of confronting something infinitely larger than ourselves. That alchemy didn't just popularize science, it reminded a generation that the universe's mysteries aren't just problems to solve, but stories waiting to be lived. The proof, a decade later, we still measure every new black hole image against Gargantua, and every discussion about space-time carries echoes of Murph's watch, because Nolan and Thorne taught us to see the science we'd always overlooked, hidden in plain sight like gravitational love letters across the dimensions. After breaking down Interstellar scene by scene, the verdict on its scientific accuracy lands somewhere between groundbreaking realism and poetic license. The black hole physics, remarkably precise so much so that Kip Thorne's equations for Gargantua spawned legitimate astrophysics papers, the time dilation on Miller's planet. Exaggerated for drama but rooted in real relativistic math, yet the film's wormholes, tesseracts, and gravity-defying love transcendence, those stretch the limits of known physics, bending the rules to serve the story. What makes Interstellar special isn't just its fidelity to science, it's how it leverages real theories as springboards for imagination, inviting audiences to ponder the what-ifs lurking at the edges of human understanding. This dance between fact and fiction reveals science fiction's unique power. It's not a textbook but a catalyst. For every student who pursued physics after watching Interstellar, there's a researcher citing its visuals in grant proposals. The film's depiction of higher dimensions didn't just entertain, it gave abstract string theory a tangible shape, making the invisible feel visceral. Even its inaccuracies sparked debates that drove public engagement with cutting-edge cosmology. That's sci-fi's secret superpower. It doesn't need to be perfectly accurate to advance science. Sometimes the right blend of speculation and spectacle can make a black hole's event horizon feel as real as the screen you're watching it on. So where does that leave us? Interstellar proves the most enduring sci-fi isn't the stuff that gets every equation right. It's the stories that make us care about the equations. Whether it's the haunting beauty of Gargantua or the gut-wrenching cost of time dilation, the film succeeds by anchoring cosmic concepts to human stakes. That alchemy turning leaden physics into emotional gold is why we'll keep revisiting Nolan's masterpiece long after new discoveries render some of its science obsolete. The real test of any sci-fi film isn't just is it accurate, but does it make us look at the universe and ourselves differently? Now it's your turn. What's your favorite scientifically grounded moment from Interstellar or any other film? The docking scene's nail-biting orbital mechanics, the eerie silence of 2001 spacewalks. Dive into the comments and share the movie moments that made you believe, if only for a few hours, that the impossible might just be an equation away. After all, today's sci-fi fantasy could be tomorrow's lab experiment. The line between them has always been thinner than we think.